Hey everybody! Today we're going to be talking about the GCD and LCM with me. Big idea that we're going to build to today. We want to be able to write the GCD in terms of the two numbers. So like if we're finding the GCD of A and B, we want to be able to write that in terms of A and B. But before we get into that, let's remember what a GCD even is. Hopefully it's not too intimidating because we have seen it before. Remember, it is a number D that divides A and D that divides B, and it is the biggest number that does this. And if it's the biggest number, we write that it is the greatest common divisor of A and B. Now, if D happens to be 1, we say that A and B are relatively prime. So they don't have any primes that are the same. Also, remember for me, fundamental theorem of algebra. You probably don't remember it by that name, but I promise. We went over it on strong induction day. So 2.4b. We covered a theorem called the fundamental theorem of algebra, and all it said was that we could write any number as a prime factorization. And so that is what I've done here for A and B, is I've written it as primes to some powers. For A, I indicated the powers with A's, and for B, I indicated the powers for B, just so that we could keep them all straight. And the way that we can write the GCD is it's going to go through and it's going to look at all these primes, so all the P's are the same, and it's going to take the minimum power because it knows, oh, like A and B both have the number 3 in it. A has 1 3, B has 2 3s. That means the GCD has to have a 3 because 3 will divide A, 3 will divide B. However, 3 squared will not divide A because A only had 1 3. So using this to our advantage, we're going to say that the GCD can then be written as P1, and then you pick the minimum power between A1 and B1. Then you multiply that by the prime number 2, and you pick the minimum between A2 and B2. And you do that going all the way down to the last prime. Okay, so that's a slightly new way to think about GCD. I don't know, I look at that and I'm just like, okay, so we picked the minimums. What would happen if we did the opposite? What if we picked the maximums? That leads us to a concept called least common multiple. It is the smallest integer so that A is going to divide L and B is going to divide L. So it's the smallest thing so that you can write L equals A times K and L also equals B times J. So kind of the exact opposite idea. We had something that divided both A and B, and now we have something that A and B both divide. So again, if we start with the prime factorization for A and B, now we would go through and we would say, we're going to take the first prime, and now we're going to pick the maximum power. Because again, let's say that P1 is 3, and we have 3 to the 1 here, and we have like 3 squared here, then we know that in the LCM, we could have a 3 squared in there, because if you just multiply A by a 3, then you'll have a 3 squared sitting over here. So we know we can attain that. But we need to have at least 3 squared, otherwise B won't be able to multiply to it. So then you go through, and you just pick off all the max powers. Okay, so then let's take this for a run. Let's look at an actual example. We want to find the GCD and LCM of 4 and 6. So what I'm going to do first is I'm going to write 4 in terms of its prime factorization, so 2 squared, and 6 is going to be equal to 2 times 3. So remember, the GCD of 4 and 6 is going to be equal to prime 1, which is going to be 2. That is the smallest prime number we're working with. And we're going to pick the minimum between 4 and 6. So the two exponents we have to choose from are 2 and 1. And then we're going to multiply that times 3, where there are no 3's here in 4. So we could think of this as 3 to the 0 power, because that's just a 1. So we pick the minimum between 0 and 1 for 3. So that's going to be 2 to the 1 times 3 to the 0, which is 2, which I'm sure you could have told me right off the bat. And then LCM of 4 and 6. I'm going to copy down a little bit of this. Duplicate, because instead of min, all I want is max. There you go. So now if we're picking the max powers, the max power would have been 2 for 2 and 1 for 3. There you go. So that's 4 times 3, which is going to be 12. Okay, that was a pretty easy example. I want to take it for a run with slightly larger numbers just to see it in action. Do you remember prime factorization trees? Sometimes they're useful. There we go. So this is going to have 75 is equal to 3 to the 1 times 5 squared. And then if we do 270, I see a 27 times a 10, which is going to be a 2, a 5, and 3 3's. So 27 is 3 cubed. Oh, nope, let's start with the smallest one. 2 times 3 cubed times 5. Okay. So now that we have that, we're going to do the GCD first of 75 and 27. So that's going to be 2. And then I go and I look for the minimum power of 2 sitting over here, which is 0 because there was no 2 up here. And then we're going to do times 3, and then we're going to look for the minimum power of 3, which is going to be this guy right here. So times 3 to the 1, and then 5, and the minimum power of 5 is this one right here, times 5. So that is going to be 2 to the 0 is 1, and then 3 times 5 is going to be 15. And then we repeat for LCM, least common multiple of 75 and, that should say 270. Now we go through and we find the maximum powers. So the biggest power is going to be this 2, or the biggest power for 2's is going to be that 2, because there was no 2 up here. And then we go through and we look for the biggest power of 3's, which is this 3 right here. And then we go and we look for the biggest power of 5's, which is going to be that 5 there, so 5 squared. And now we've got like 27 times 75, no, times 50, which is 1350. All right, there you go. That is GCD, LCM, a little bit more intense. Okay, honestly, GCD gets used all the time. If you haven't been able to tell because you got to see it, you haven't seen LCM yet, but we've seen plenty of GCD at this point. GCD is really popular and it gets used a lot, but LCM is kind of like the family member would be like, yeah, remember LCM? Yeah, what are they doing? Oh no. He doesn't get used as much. I don't do number theory, so I'm not entirely sure why that happens, but I know GCD is going to be really popular. But that being said, after hating on LCM, he did do one really cool thing. We get this really cool theorem that I like. So I'm going to go ahead and I'm going to prove it. Didn't even read it off. If you multiply A and B together, then it is going to be equal to the GCD times the LCM. So let's start. This is not a proof that I would think that you could come up with on your own, just to clarify, because like honestly, the first step is just kind of like, what do you do? I'm going to tell you. You're just going to say, let the GCD be equal to A comma, or of A comma B be equal to D. And then now that we have this, we know from the definition of GCD that D is going to divide A and D is going to divide B. And then we know what divides means. We can write this as A equals D times A naught and B equals D times, we'll say B naught. Just so that we can, easy notation to keep track of where A naught and B naught belong. And then furthermore, since D is the GCD, that means A naught and B naught can't have anything in common. Otherwise, it would have had to be here in D. So we get to say that the GCD of A naught and B naught is 1, so that they'll be relatively prime. Okay. Now that I've said this is where we want to start, what is the goal? What do we want to say? I'm going to do some quick math here in red that's going to get erased just to show where we are about to go. I know that A equals D times A naught. I know that B equals D times B naught. If I were to multiply them together, I would get D times A naught, D times B naught. I know that this part is the GCD, which means if it's going to be equal to the GCD times the LCM, I've got to prove that this other piece is the LCM. So that's where we're headed. Okay. With that in mind, let's start with, we know what a least common multiple is. It means A is going to divide that number and B is going to divide that number. Note that A divides A naught D, or let's write it D A naught B naught, because this part is A, and B divides A naught D B naught, because this part right here is B. So since B divides B, it is certainly going to divide an integer times B. So since we have this, we know that it is a multiple. So then A naught D B naught is a multiple of A and B. Is it the least common multiple? Don't know. That's what we have to prove. Once we have that, we'll be done with this proof. So how do we prove that this is the least common multiple? Well, we start with another multiple, and we show that it's going to have to be bigger. So we'll say let M also be a multiple. Be a multiple of A and B. Why did it do that? I'm not allowed to change pen colors right now. Okay. So if it is a multiple of A and B, that means we're going to be able to say that A divides M and B divides M. So quick reevaluation of the goal. We want D A naught B naught to be less than M. Since M is another multiple, we want it to be, or less than or equal to. We'll settle for equal to. One way that we could get this is if maybe we could conclude that d a naught b naught divides m. Certainly, m would have to be bigger if that number divides. So can we get to here? We can if we do the correct substitutions using the information that we have right here. So what we have, a divides m, so m equals a times k for some integer k. But b divides m, so then I can substitute that in right here. So b divides ak. We know things about b and a in terms of the greatest common divisor. Remember, we had other definitions for a and b, so let's go ahead and do that. So then we have db naught divides da naught k. And then from division rules, we know that these d's, since they're not zero, thankfully, I mean, you can't divide with a zero, we can get rid of those d's. Those cancel out. So now we're left with b naught divides a naught times k. We know how b naught and a naught are related. We know that their GCD is 1, which means b naught is not going to divide a naught. So then b naught has to divide k. But if b naught divides k, that means we can write it as k equals b naught j, where j is an integer. Okay. So let's step back. What have we gotten to at this point? We have gotten that m equals ak, which is really just, here, I'll leave that, ak, which is really just d times a naught times k, where k is just d times a naught times b naught times j, because that's what k is equal to. So then, here you go. We have the number that we were looking at times an integer equals m, which we know the definition of divides, so then d a naught b naught divides m. So then d a naught b naught is less than or equal to m. And I really wasn't being careful. J is going to be positive. Like, what if J is negative? Then it's not less than technically. No, it would be positive because AB was positive to begin with. And so everywhere you find Z, you can just put a positive on it. Okay. So what have we proven at this point? So D A naught B naught is a common multiple of A and B, as pointed out right here. And it's the smallest one. Okay, so that sounds like the LCM of AB is now equal to D A naught times B naught. But what were we really going for all along? We were going for what A times B is actually equal to. So we can say that GCD of AB times LCM of AB is equal to, the GCD was D, And then we've proved that the LCM is D times A naught B naught. But we know that A naught times D is A, and B naught times D is B. So we get A times B. So again, this is like, I think it's kind of cute, kind of fun. Shows how much fun my life is. And it's, I think probably the coolest result that you have for LCM. And so I did want to walk through it. It does require a lot of innovative and creative thinking. I don't think that you should struggle with any individual step. But if you're like, oh my gosh, how could I have come up with that off the top of my head? You keep doing math for many more years. That's how you can come up with it off the top of your head. I would not expect you to come up with it off the top of your head, but I do expect you to be able to follow this. So hopefully that is where you're sitting at right now. So now that we've done GCD, we've done LCM, remember the goal of today was to write the GCD in terms of A and B. So let's bring in another tool that is going to help us with that. We're now going to talk about something called the Euclidean Algorithm. I would like to draw your attention to a fact that we're about to use. It is on your final exam question bank, and so I would even recommend pause the video, prove this fact. Now you've done a question from the final exam question bank, which can only be a good thing, and it'll make your acceptance of what I'm about to say probably a little bit better. So since we can say that the GCD of AB is equal to the GCD of B and the remainder, if we use the division algorithm on A and B, we're going to use this to our advantage and keep repeating. So we're going to, step 1, apply the division algorithm and find our R. That means, here, I'm going to do it like alongside with this next example. I think that's probably going to be best. So then we could say that 270 equals 75 and then times 3 plus 45. That means that the GCD of 270 and 75 is going to be equal to the GCD of 75 and 45. But the GCD here, we can do the same thing. We can do division algorithm on these two numbers. So now you do 75 equals 45 times 1 plus 30. And that's what this second step is saying to do. So you put B as the dividend and you make R the divisor. Here, I can color code that a little bit. So put B as the dividend and then get a different color and R is the divisor. There we go. And then we just keep repeating this process because now we have GCD of 75 and 45 is equal to 45, because 45 is the new B and 30 is the new R. So now we move, we say 45, our B gets moved over here, our R gets moved, and then we find our new R. So times 1 plus 15. Back to the original point though, I wanted to write the GCD in terms of the two original numbers we were looking at. Can we do that? I'm going to remind you that we did a tiny version of this. So you guys totally remember worksheet 1.5b, I'm sure of it. Just in case you don't. Remember, we wrote 1 as a combination of A's and B's when we were given that they were relatively prime. You guys proved this on your worksheet. What we're going to do now is I'm going to generalize that lemma into Bezout's theorem. which says doesn't matter what the GCD is, you can write it as a linear combination of A's and B's. We are not going to prove it because it is not particularly enlightening, and I don't have time to do that in my life. So with this in mind, we want to write the GCD of 6 and 10 as a linear combination of these numbers. Yes, I can pick out the fact that the GCD of 6 and 10 is 2 right off the top of my head, but we want to do Euclidean's algorithm because that's going to be very helpful here in a second. So we've got 10 is equal to 6 times 1 plus 4. So then the GCD of 10 and 6 is equal to the GCD of 6 and 4. And yes, I want you to write out this whole side-by-side GCD thing because I think it helps keep everything straight and in place. Oops. So now if we move 6 and we move 4 and we find our new remainder, which is 2, we can say that the GCD of 4 and 2 is the next one we're working with. So then now it's going to be 4 equals 2 times 2 with no remainder, which means this last number here is our GCD. So it's 2, just like I suspected all along. Oops. Something else that I can do off the top of my head by just looking, I can write 2 in terms of 6 and 10 very easily because 12 minus 10 is going to be 2. However, things like your worksheet are going to be much more complicated. So you probably want a more algorithmic way to do it. So what I'm going to do is I'm going to say I know things about 2. I'm going to use this line right here to say I know things about 2 that are in particular related to the GCD in some way because I did start with 10 and 6. So let's use this for now. So 2 is equal to 6 minus 4. Very specifically 6 minus 4 because that's what that equation says. And then now I'm going to say 4 is the next object of my wrath. I don't like 4. 4 was not part of the original deal. I want back to 10 and 6. Great news. I have an equation relating 10, 4, and 6. So 6 minus, and we're going to say 10 minus 6. Be sure to distribute your negatives. Now we have 2 times 6 minus 10, just like I originally predicted. Let's take this for a run when it's not obvious. Let's write the GCD of 75 and 270 in terms of 75 and 270. We already did the work for finding the GCD using Euclid's algorithm, so I went ahead and copied that down. So now we start with the second to last line, which is going to give us an equation involving the GCD, which was 75. So we're going to say GCD, or GCD, it was not 75, it was 15. I know my numbers. Was equal to 15, which is going to be equal from this equation right here to 45 minus 30. And then I'm going to back up. I'm going to use this equation now. I'm going to say I'm going to replace 30 with 75 minus 45. So then we have 2 times 45 minus 75. And then I know I can replace that 45 with stuff from this equation. So that's going to be 2 times, and it's 270 minus 3 times 75 minus 75. Notice I keep like the 3 separate from the 75. That way I can play this coefficient game with the 75. So this is going to be 2 times 270 minus 6 times 75 minus 75, which is really just 2 times 270 minus 7 times 75. So there you go. Our coefficients are -7 and 2 this time around. There you go. We have expressed the GCD in terms of the original A and B. And that's what we came to do today. And so I will leave things here. Talk to you guys later. Bye.